Okay, I'm going to continue down this path of talking about, and you know what, I'm going to unplug this and then I'll plug it in here in my next class. Out there, I've got two classes back to back, so I have to plug my laptop in. Otherwise, I probably won't make it through the 4 hours. Although I won't talk 4 hours anyway. I'll talk about an hour and 50 minutes. There. Okay, I'm going to continue down this path of talking about counters. And I'm switching books again, and I know this gets relatively confusing because I am using two books that there. And as I said before, I've got my reasons for using two books because both books, between the two of them, one will cover some topics better than others. That there, you've got copies of both books. The only problem is I'm switching back to the Tochi book for this discussion, and the Tochi book likes to draw his counters opposite direction of the Floyd book. If you look at this counter here, he's bringing the clock in on the right side, and this is A, B, C, D. And some, and what just happened there? Okay, that's going to be interesting if that's going to continue to do that. Right there. Well, you can see what I'm saying. This is A, B, C, D. When I was using the Floyd book, he was bringing the clock in on the left side, and the least significant bit was on the left. In some ways, this is a little easier because it's the way that you would write it, but it's opposite of what I did. So hopefully that doesn't confuse folks too much right there. And we're going to jump into the area of synchronous counters today. Right there. We talked a little bit last time. This happens to be a counter if all the JKs, the ripple counter we looked at before, if all the JKs are tied high, I'm not sure, this is an up counter right here, so this is not that there. And are all assumed to be 1, and we're clocking on that there, and for whatever reason that's wanting to do that today, that there, but these are clocking on the down edge, right there on the JK. And as we're going through here, he's using that there. But this is showing that these are changing states exactly at the same time. We saw that later on that doesn't happen. That we had this effect that the book talks about here. And I already covered the ripple counter to a degree. But as you notice here, this is showing a 50 nanosecond delay. Then it becomes 100 nanoseconds, then it becomes 150 nanoseconds. The larger we make these ripple counters, the larger the delay is when we have all the, when we have this output change, C output. Now, we've been using the Altera part. In the Altera part, typically the delays are more around the 10 to 15 nanosecond range, or less. That's there. But this is, if you're using TTL parts, a 50 nanosecond delay is not uncommon. That's there. So that could be a problem. That's there. I have worked on more than one project. That there. And remember, I like to ask questions about that there. And how many more weeks do we have left? Because I need to do a review of the final for during the last week. That there. Well, we'll talk about that later. Let me finish the topics, but. Don't let the end of the semester sneak up on me and I haven't reviewed for the final, okay? Don't let that happen, because I have 3 schedules running overlapping and simultaneously. I had the short semester this semester, and this one's kind of overlapping, and then I have the regular September semester. So I have no idea when this class really ends off the top of my head. So keeping track of all those, I may let it slip up on me. We're all right on material, but what we're looking at here as we go through here, and if our clock gets shorter and shorter as we increase its frequency, in this slide here does a good job of showing here. Here we have a clock that's only 100 nanoseconds, right there. And here we have a 150 nanosecond glitch. So when we speeded this thing up, we completely lose that last transition. It disappears. And I think some of you, when you run the Corda software, the default is 10 nanoseconds on the grid size, and I always have you change it to 50. That's to avoid that problem right there. So one of the things we run into with asynchronous counters, and this is an asynchronous counter, and the term asynchronous means that they have different clocks, or that things aren't occurring on a clock edge right there. When we have these different counters that are different clocks there, we end up with these transitions that occur at different times. They may work perfectly fine in some situations, but two things can happen. That there is, one is your clock frequency changes right there. You were operating, let's say, at 150 nanosecond clock, and then you go to a 50 nanosecond clock. In other words, you speed up the system for various reasons, and that's not uncommon in today's society. Today's digital electronics. We're always trying to get the maximum speed. Now, that occurs, or two, some of the component changes. This is more likely to be the case right here. We've got components that operate very slowly. It takes them 10, 15 nanoseconds to react. These glitches don't cause problems. A part goes bad, that part number is no longer available, so they buy a part that's pin compatible, functions just exactly the same. According to the data book, it looks that there, but the new part is much, much faster. So it sees those glitches and reacts to it and causes errors and malfunctions. I've ran across, not this, because this is a design change. So if you're going to change the clock frequency, you're going to go in there and you're going to check the design and make sure it's valid. That doesn't happen accidentally, right there. And you would test it at the higher frequency and you would make sure all your circuits would work. Now the only thing is that a clock frequency might change as you change to newer technology, and then you realize that your old design's not going to work because it uses asynchronous inputs and clocks, and you have to do a complete design where it was designed correctly the first time. You would just update the technology and speed up the clock. So you would have to do a total redesign, but it doesn't happen accidentally out in the field. Although people do have a tendency, and they'll push it to the limit until it malfunctions. And I always get a negative to this question in other classes, but maybe this class is different. Is anybody here a computer geek? Puts computers together to play games and tries to optimize computer hardware? Okay. So I call them the computer geeks. And I'm used to a lot of those in my technology and engineering programs out there in the U.S. Because those are the kind of people that tend to go into engineering. Here, of course, people are kind of pushed into engineering, or they go into engineering not because their passion is so much into the technical world. So those people will take motherboards they buy a computer motherboard and processor, RAM, and everything else. They put their own system in there, and they get in there and they start tweaking the clock, and they overclock it. The term is overclocking. And they'll keep overclocking until the system malfunctions. And that's a tendency of particularly computer gamers that know hardware. They like to overclock their systems and push them to the limit till they start malfunctioning. And of course, if they push them too far, then they have to take the case apart and they have to do a jumper to do a full reset on the motherboard and back to defaults and everything else to come up. So you do find people that do tweak the clock in systems to get a little bit better performance. And you find that in commercial systems too, not just computer gamers. This thing's operating at a 5 gigahertz crystal. Okay, it's working fine, but we need a little bit more performance. Let's put a 6 gigahertz crystal in there and see if it still works. So there's folks that will do that with existing hardware to try to improve the performance. Tweak the clock, or overclock it is the term most commonly used. This one I've ran into far more often is that we've got a system out in industry that there. The worst case I ran across to that was a system we had that did something very, very high tech. It counted eggs. I mean, when I say very high tech, it counted from 1 to 12, and then an arm moved over to fill an egg carton. Eggs are sold by the dozen in the U.S. and Canada. And I think Malaysia, they sell them in boxes, 10? Right there. If you buy a box of eggs at Carrefour, or it's not Carrefour anymore, Eon, it's 10 eggs in a box. In the U.S., it's 12 eggs in a box. Regardless, it would count to 10, and then the arm would push it over, and then it would fill up a box of eggs. So that there, and it was working perfectly fine. One of the chips in one of the factories, one of the chips went out. They couldn't buy that chip anymore. They went out and bought another chip that was a same chip. It was a 74, but the original design called for a 74. I think it was just 7439 or whatever, 7432, whatever, out there. And they couldn't buy a 7432 anymore, so they bought a 74 LS32. Same package, same pinout, same function table, drop-in replacement. Well, unfortunately, because the original design was sloppy, it didn't work. That there. Actually, we found out later that the processor was obsolete. We had to do a redesign anyway, but still, we had to go back and redesign the board to accommodate for faster components, because if they replaced that there, so you could no longer just put a drop-in replacement. So typically, asynchronous designs are bad. That's a general rule. But the reason they're bad is they're relying on consistent hardware and consistent delays in some cases. That there. Timing. Things change as they age. Resistors change. Motherboards change. Or PC boards change. Capacitance change. So when we look at propagation delays, right here, the delay here between here and here, that's our propagation delay. That is not always just a function of the IC itself. That can also be a function of whenever we have something going out of a board, going into it, we have some stray capacitance going here, and we've got some resistance here, right there. Now this is part of the circuit board. It's not part of our design. That's part of the circuit board. It can be the solder connection between the board and the motherboard, or the board and the IC, that creates resistance right there. The actual lead itself, on the PC board creates resistance. Between the board and a ground, there's a space right there. Right there. And if you remember what makes a capacitor, it's two metal plates that are in parallel with each other. And with some kind of non-conducting dielectric in between there. When you have two parallel traces of wires there with board in between there, they form a capacitance right there. And that's why parallel communications doesn't work so well at high speeds, because when I run 9 wires through a cable, all in parallel with each other, I've got capacitance in between. As I increase the frequency, as you remember, capacitance right there, when we look at the x of z right there, at DC it's infinity. As you go in frequency, the impedance goes down. If x of z is equal to 1 over minus j omega c, right? Or omega RC, right there. So as we look at, or no, not RC, that's omega c, right there, minus 1 omega c, right there. So as we go up in frequency, that impedance between those wires goes down. So as we look at this, there's all kinds of problems with asynchronous, because the output or the output capacitance of the pins change with time. The board becomes older. It picks up corrosion on the outside. It might get a layer of dust on the outside, on the coating of the board. It might get damp. In Malaysia, we get a lot of rain. things get damp, the resistance of the solder junctions might get old, the resistance may get higher. So things change as they age. So the secret is we come up with systems that change only on clock edges. That's there. We use a common clock for all of our counters. And that's what the next series of circuits does here. And this is a synchronous parallel counter right there. And this is a circuit. Now this is a 4-bit circuit. Let me talk about how this one works. And you'll be expected to regurgitate this one here. Now, before I talk about this here, let me just kind of look at here. This is my least significant bit right there. So I'm going backwards. Now all the clocks are tied together. And I don't know what my computer is doing. My computer woke up without the coffee this morning. I've got my coffee, but the computer hasn't had its coffee yet. That's there. But regardless, all these use the same clock. That's there. Now, on my least significant bit, I tie 1 to J and K. My next one, I don't tie 1 to J and K, but I tie the output A to J and K. My next one, I tie the output ANDed with these two ANDed together go to J and K. This one here, I have them all ANDed together. Now the reason for that, and I'm just going to use this truth table right here, is that if we look at A changes every clock pulse, right? A changes every clock pulse. B changes only when A is high. There. You see A is high, B changes on the next clock. A is high, B changes on the next clock. If A is 0, B doesn't change. A is high, B changes. A is high, B changes. A is high, B changes. So a JK flip-flop toggles if and only if both J and K are high. If they're low, it doesn't change. Now let's look at C. C changes here, changes here, changes here, and changes here. In every case, and I'm sorry for this here, this is, for whatever reason, I think I need to clean my screen is what it is. The screen is up there. But C changes at these lines. That makes it easy, so right there. In every case, both A and B are high. Here, both A and B are high. A and B are high. A and B are high. So we can use those there. D only changes when all three of them are high. That there. So if we use that as our key right there, if we look at this right here, 0, 0, 0, 0, 0, 0, 0, 1. Okay. This is A. It changes every clock cycle. If we tie here, A is high, so B will change, and A, of course, changes every clock cycle. So I'm just going to go ahead and try to write this out. 2, 4, 6, 8, 10. All right, we'll take it down this far here. That's there. So here A is low, so B doesn't change. Here A is high, so B changes. Here A is high, low, so B doesn't change. So I'm looking from here to here, right there. Right there. I'm going in that direction. So A is low, B stays the same. A is high, B changes. So as I go through and look at this right here, right here, right there, we see that pattern there. So here, these are not, both A and B don't change to right here. See, here they're high, so all the way through here, and here, excuse me, I went too far. Here they're both high, so here it's going to change. And they stay the same until, and I got this messed up here. Right there, okay. So here it's going to change. Here it's going to stay the same, here it's going to change, and here it's going to change right there. There, right there, and that stays the same. So what we're going to see here, there. So what we can do is we can design a relatively simple counter by just using AND gates right there. And the design is fairly straightforward right there. Our first D flip-flop, or JK flip-flop, these are all using JK flip-flops. JK, we tie to VCC, and we take our clock in right here. Right there, there's our clock right there. So that was going to change every other one. Now we take our Q out right there, and we tie that to our next flip-flop, and we tie that to J and K right there. So if we do that, we're going to count the sequence 0, 0, 0, 1, 1, 0, 1, 1 right there. We're going to see that count, that sequence, and then the next one will, of course, go back to 0, 0. So if I put this into Fortis, that's what I should see. And the problem is I run out of space, this resolution here. My Quartus is, oh, there it is. I was almost sure that I put it on my start menu there. I hate looking for it every time. So we're going to go through and look at these right here. And actually today's goal is to get through these types of counters, and then when we come back from the break, I'm going to go into VHDL and finite state machines in more detail. Right there. So as we go through here, now I'm going to draw this, unfortunately, the same way that Floyd does, because that's the way that the software is going to do that. So let's go ahead and block diagram. So if we put in a JK flip-flop, and actually, yeah, I'm going to go ahead and use JK flip-flop here, right there, and it's got getting cold with the aircon and the fans, right? Okay. All right. If I use a JK flip-flop, now remember that I'm going to have to put inverters on that there, and these don't have Q not out. That there. I could go back and let's see if the book here gives me a part number here. This particular book doesn't give me a part number. Unfortunately, the software doesn't have built into it this exact flip-flop right there. So, all right, so I'm going to go ahead and use this one right there, and let me just go ahead and put 3 in for right now. And I need to put plenty of room in between there because I need to put a knot. You know what? To be quite honest, I'm tying all the clocks together so like one knot gate is all I need. Right there. So we do that there. So I'm going to go ahead and tie VCC to the first flip-flop. Right there. And I'm going to tie Q to here. I'm going to put in an and 2. And I'm going to tie that. One input of the and 2 goes to here. The other one comes to here. And then J, K right there. I'm going to tie all my clocks together. I'm going to bring in a clock input. Right there. And now my outputs, I'm going to just right here, and I have it tied this J to here. Okay. Right there. And now let's go ahead and put in our outputs. And I'm just going to put them underneath here. Now the other thing I need to do is I need to tie and this gets really ugly. I hate to say it. There. All right. So, oh, we're not connected. So all my presets and clears are tied together. All my clocks are tied together. And now I need to tie my cues together, or to my output. I made a mistake here. Well, okay. Now, that looks right. Does it look right to everybody there? What? It does. You saw the mistakes I was making there along the way, right? That's there. Okay. So, this is clock right here. Now, this is A, B, C. A is our least significant bit in this particular case. So I'll keep that in mind that I did this ABC That there. This is my most significant bit. So when I write the table, it'll be CBA. A is, or no, excuse me, I got that wrong here. C is my least significant bit. A is my most significant bit. I'm getting confused with the Floyd Tochi mix up there. So now when I run this clock right here, right there. So let's go ahead and save this. And one of these days I'm going to go through and clean out my design directory and delete everything in here, because they're all examples that I've run for various classes that there. But let's go ahead and say adder 3-bit sync right there. I'm going to copy that just so that right there. And I'm sorry for this, but and guess what? Okay. I screwed up and it saved up under the wrong name. So, okay. So there's my file right there. It actually, to be honest with you, the reason it's so ugly looking is because I try to fit it into one screen on this up there. If I spread this out as I normally would, all these outputs would be over here and the inputs would be there. I've compressed this so it would fit on the screen that way up there. So let's go ahead and compile this. And I probably should have brought a board with me. Actually, one of the things we have to do if we're going to do this with a board is, because I got a little bug here, is that I saved it by the wrong name initially, then I deleted it. Project it was looking for a file called block. I forgot to change the name of the file. Now, go ahead and simulate this. So file create, new vector waveform file. Again, remember that end time, we said, I just do 5. It doesn't matter how long you do it, that their value, or grid size, it's this 50 that really matters, right there. Node finder, list, right there. And then here's our clock, value, clock, right there. So now we're ready to simulate this. Save it. Right there. And if we look at here, again, C is our least significant bit that there. We're seeing what we're counting, and I'm not going to go ahead and put the group, I'm not going to bother grouping. You can see the values change here. This is 0, this is 1, 2, 3, 4, 5, 6, 7, and back to 0. Now notice here, let's just look at this point right here. All 3 of those are changing. Right there. Right there. They're all three changing on this trailing clock edge, but they're changing pretty much all at the same time, right there. If I did the ripple counter, they would be changing. A and B change exactly the same time. For whatever reason, I'm trying to find a place where they all change. This one changes slightly below that there. But this time difference between here and here right there, you can see is about 9 nanoseconds there. Right there. You know, from the clock to the change, you know, here's our clock change. The time difference between here and here is about 3 nanoseconds. That's getting pretty picky right there. That's pretty much the same time. If we did this as a ripple counter, you would find that it would take much longer. Now, we could go through and we can expand this clock fairly easily. If I wanted to expand this, all I would do right here and is put another JK flip-flop in there, tie another 2-input AND gate right there, and tie everything. So I'm just going to go ahead and put in one called Z. That'll be our least, because A right now is our most significant bit, right? No, excuse me. A is our most significant bit there if we shrink this down. Right, A is our most significant bit there. If I put another one, I'm going to call it Z, and I'm just going to show that all I have to do is add one more flip-flop and just carry the pattern out right there. So I'm going to go ahead and do that. In this particular case, I need to add a JK flip-flop right there. I'm going to just stick it here. Right there. I'm going to go ahead and tie those there. I'm going to go ahead and put in an and 2. Hopefully I gave enough room for it there. Not really. I'm going to move it over a little bit. Because what I'm going to tie this to is this and 2 and this Q right there. Take J and K. Connect the clock to the same clock. Right there. Put in one more output here. Output. I'm going to stick it right here. And I'm going to call it AA to just show that it's one after the A that's there. So again, this is the same. All I've done is just added one more flip-flop and just carry the same pattern right there. All right, and then we go back to our vector waveform. We need to add, and I can just say AA right there, and I'm going to move that actually I want to move it to the top right there. So I've added that one there. I go ahead and save it, and I resimulate it. One warning. Ignored vector in waveform. Can't find AA in design. Okay. Oh, I added that there. I shouldn't have to recompile. Okay, what's going on here? Did I think I forgot to recompile after I added the pins up there. What are my warnings right here? Warning, that there. Reserved all pins. Output capacitance. No exact pins. Block. I thought I deleted that. Remove. You know what? I deleted it and I forgot to hit the OK. Because I think you can't see the OK with the screen there. Okay. Okay, now it saw it. I didn't recompile. But notice now again that if I carry this all the way out, it's now doing a 16-bit or a 4-bit add. And it's performing exactly what I was expected to see right there. So it's doing what I'm doing. I can add a 5th bit. I can add a 6th bit there. So this is the pattern that, and actually, as it turns out, I believe I can take this inverter out and it doesn't change right there. Let's take the inverter out and we'll see that it just changes where it shifts. Right there. I could be wrong. I haven't done clocks this way in a long time, counters that way. You'll see when I get into VHDL why it's so much easier in VHDL. That there. So, and then I need to simulate. There, and you'll see that it's still behaving the exact same way, only just changing on the rising clock edges instead. So I'm still counting up right there. I go 1, 0, 1, 2, 3, 4, 5. Here, this is 5 right here. 6. Here's 5. Here's 6 right there. There's 7. I go to 8 right here. This is where my 4th bit changes. And we can see that we get all the way here to, they're all high here, and then they go all low here. And again, as you can see, they're all changing pretty much at the same time right there. If I tried doing this with the ripple, you saw that staggered right there. So this is a much better performance type clock there. Now, the next question is, what if we want to count from 0 to 9? Right there. And the way that we count from 0 to 9 is we decode our first illegal state. Right here. This counter counts from 0 to 15, right? 0 to F, right there. I want to count from 0 to 9. I have these 2 pins in there called reset and preset, right? So if I want to count from 0 to 9, what I can do is I can decode 10, which is 1010, right? Is that, yeah, 1010. That's the letter A. That's 10. That's my first undesired state. I decode that and I use my clears to reset it right there. Now I'm going to probably cheat on my drawing and name some nodes to show that. But what I'm going to basically do is I'm going to have an AND gate that's going to have in it, and my most significant bit was AA, right? AA, A, B, and C, right there. So that's going to decode 1, 0, 1, 0, and I'm going to take that to my clear NOT. So this has got to be a NAND gate right there. So I have to use a NAND gate. This is my clear NOT right there. So I need a NAND 4 right there. So what I'm going to do is I'm going to redraw this to show that it will show the 10 for a very brief glitch, but then it's going to immediately reset all 4 flip-flops right there to the number 0. So it'll go from 0 to 9 there, and then it'll start to go to 10, and then it'll go right back to 0 right there. So when I do that right here, and I'm going to shrink this down a little bit. No, going the other way here. And I realize that it's impossible for you to see that there, but first off, I'm going to disconnect these clears. See, here's this clear right here. I'm going to disconnect that from BCC right there. And then I'm going to rename this node clear NOT right there. Right there. So I name that node clear NOT so I don't have to draw a line to it right there. And then I'm going to rename all these right here. A, B, C, AA, right there. The reason I did that is that I don't want, and I did this earlier in the semester, I showed an example where I named the nodes where I don't have to draw that there. All I have to do is I can put in a NAND 4 right there. Right there. I'm just going to stick that in down here at the bottom. And I need 2 NOT gates. Right there. I'm going to move this out here. And I'll explain what I'm doing here when I finish. Right here. Right there. And I'm going to bring this in. And I'm going to call this AA. Call this A, B, and C. I don't think this one's connected. Yeah, now it's connected. Okay. So all I've essentially done is, by putting that there, is this AA wire is connected to this AA wire down here. Right here. Because I gave them the same name, but the same thing is internally connecting them. So I don't have to draw this thing. The drawing's going to get ugly right there. So, and then I've tied together all my clear knots should be, and I did name that, right? Yeah, right here it is, are all tied together to this clear knot here. So now when I compile this, and this will tell me whether or not I got all the nodes connected together. If they're not, this will give me an error. It's missing one of the names. And obviously it's not giving me an error, so I got them all connected. Right there. It's just a way to save from drawing. And actually what you'll see is I can go back and I can change easily that 4-input NAND gate and count to any sequence that I want to count to. So now when I simulate, right there, go to my simulation report. What we're seeing right here is we get here to, this is 1, 0, 0 here, right there. We see our 10 show up for a brief pulse right here, but then it goes right back to 0 right there. And then if we look at this pulse, we're going to find that as pulses go, this is about 4 nanoseconds right there. So 4.5 nanoseconds right there. And by the way, I'm pushing the button right here, and then I'm bringing it over here, and that tells me what, I can read there the interval there. So that tells me how wide my pulse is. So that's how I'm measuring the pulse width there. So now if I want to count to, say, another sequence, I want to count to 12. And 12 is 1, 1, 1, 0, 0, right? Right there. So I would decode 13. So let's go back to my drawing here. First of all, let's go back to here. And I want to count to 12. Right there. 12 is... And my pen, everything is... Uh-oh, this could be... I've had a couple of days where all my technology has failed me, and today has actually been pretty good, but this battery I just replaced about 2 weeks ago. The first battery lasted me 8 months, so this battery shouldn't be dead already. Actually, they make these that have so I don't think it's a battery. I think it's just my... Okay, so we look at the number 12, and the number 12 is 1, 1, 0, 0, right? So 13 is 1, 1, 0, 1. So this is the one we want to decode right there, is 1, 1, 0, 1. So all we need to do is put in our NAND gate, AA, right, to C, is we only put an inverter on this one right here. So all we do is go back to our circuit, right here, and we said we need an inverter here, right? So let's delete this one. Let's delete this one. Go ahead and wire these up. I'm going to delete this B right there. Actually, I'm going to delete that whole net. And the reason I'm deleting that whole net is because I need to put B back in here, but I need to put the inverter in first. Right there. Okay, we just simply recompile it. All I've done is just change the inputs to this 4-input NAND gate, right there. And I can have this, I can change the end count very easily by just changing that NAND gate. And simulate. Right there. And what we'll see right here is, here's where we reset. This is the count 1101. Hold on. Did I do that wrong there? Yeah. Okay, now, okay, this is 1101. Did I put the NAND gate on the wrong place? Because this is 11. That there. Because this is the rising clock edge. A goes there. It looks like the because this is 1101 right there. It looks like it should reset 11. Oh, I'm going the wrong direction here. 1110. This is 11. I think I should be inverting. It looks like I made a mistake somewhere here. This is 1100. So the next one should be 1101. Right there. This is AA. This is C, right? What have we got here? Here's 110. Why is AA not changing? Ah, I see. I got these mixed up. C, B, A, right there. I got it backwards. That there. Good place to wrap up here as I start making these silly mistakes. So my inverter should be on A, right there. So that's where I mess up. My inverter should be on A. That's why it's not working. So we delete this. I'm going to delete this little wire here. We put the inverter in here. I need to start bringing a real mouse with me here. Trackball is even worse, I think. Yeah, that's even worse. Trackpad. Excuse me here a second. Part of the problem is the screen resolution is what it is, and the mouse resolution is much tighter than the screen resolution. Right there. This screen has got like 2,500 pixels by 1080 or something like this. It's an unbelievably high resolution. in comparison to this thing here. So, right there. Okay, now let's try recompiling and resimulating it one more time. And then I'm going to say that and lo and behold, here's our 1, 1 right there, and we count 1. Here's 1, 2, 3. There's 1, 0, 1, 2, 1, 2, 3, 4. I need to ignore this clock here, right here, because we get to 1, 1 right here, and then we go to, we need to go to, yeah, right here is where we set it, reset right there. As soon as this goes high, right there. As soon as we try to go to 13, it looks like actually my inverter up there. I'm doing something wrong with that there because it's still not looking right to me. Because A is our most significant bit, and as soon as that tries going high, it stops there. You know what? It's decoding. One, 1, 0, 1. It's picking up a glitch and resetting too early. That's there. That's one of the problems, is that a glitch will screw this thing up. I'm going to stop at this point. It works at 9, but the 12. Let me just bring the circuit, bring it back up again here real quick, and show you what's happening here. Right there. Something's happening there, and it's not the first time I got in front of a class and something wouldn't work right. I think it's not the first time with this class that's happened. That there. Well, some instructors come in with a pile of notes that there, and they rework every problem. I tend not to do that because one is I go too fast, and two, it's that there. But when I'm trying to do this in software without having it pre-done, sometimes it will create okay. Let's look at it one more time here. You know, actually, let's go through here and let's group these together. Group. Most significant on. See, we're counting to 4 properly. 5. You see, and at 7 is our glitch, is where it's screwing up right there. When they're all supposed to be changing at the same time, remember I said that they're not all changing at the same time. There's that one little that's there. If we were to expand this out, we would see somewhere in this group here, it's going to go to 13 for a short. It went to F here. It went to E for a short period, right there, and it may even go to D for a short period. There, it went to C for a short period. So you're seeing all kinds of glitches occur in that time frame, and as a result, right there, it's going back to zero. That's when I mentioned the risk of glitches. Right here is a classic case where a glitch got me. Right there. This would probably work okay in discrete chips, but because Altera picks up that glitch so quickly, it grabbed that very short period where it saw 13 and reset it. That there, because it's supposed to go from 7 to 8. But when we look at this right here, between 7, as we're going through here, we're seeing all kinds of short little glitches happening in there. Up there, there it is. Right there. See, it's supposed to go from 7 to 8, and it does, but that there. However, in this short little period that it went to 8, there was a period just long enough right here, because you see that went to 8 there properly, but during that time, for a short period, it went to E, F, and E. And E is what number? Right there. X. E is 14. F is 15. Right there. So it went to a short little period, which it caused that glitch right there. So if we go, because it's looking for decimal 13, which is D1101, which we had that right there. But so somewhere in this group here, you'll probably find that there's a D popping up in there somewhere. And that's all it took. And to be honest with you, I can't fix it. Because that's just the nature. You're not going to be able to do it with this technique. And this is one of the reasons why we don't necessarily use this technique that much. Because it's requiring an asynchronous reset, looking for a particular input. And that requires that our outputs change completely. Nothing is perfect. So I didn't do anything wrong in this particular case. The hardware just will not work for me, and this is a common problem that engineers run into, is that I followed all the rules. If you go through the book, it goes through the steps on how to do this. I follow those rules exactly. It doesn't work. It does not work. And why doesn't it work? Is because it's not 100% synchronous. And this hardware is so quick, it caught that little tiny glitch and did the reset early. That's there. So, valuable lesson there is that sometimes things don't always work. That's there. And this is the case. It didn't work. Yeah. And you'll find, go out, if you do work in the design area or even the maintenance area, it should work. It should work. It should work. It doesn't work. It doesn't work. It doesn't work. Why isn't it not working? That's there. And I looked at this multiple times. Why isn't this working? And then when I saw those glitches in there, yeah, that's why it didn't work. That there. And I was going to stop there when it didn't work, but then I thought it was worth the time to go back and show you why it's not working and tell you why I can't fix it. I can't fix it using this hardware and this technique. That there. This design technique does not work in this particular case. It worked on 9 because there wasn't any bad glitches there. But in this particular case, it picked up that glitch right there. And that is one of the things that will drive a design engineer to sleepless nights sitting there looking at this here. As it turns out, VHDL and Verilog solves a lot of these problems. That's there. So that's one of the reasons we tend to use those techniques versus trying to do it this way. Right there. So, all right. With that said, I'm going to say, have a good vacation or holiday. It's not vacation. I am going to stop at this point right here when it's 5 minutes shorter than normal, but that's all right.